Hi everyone, and welcome to the first of two videos going through some past exam questions on the topic of enthalpy changes. So if we look at this first question, we've got a reaction here. They've given us the enthalpy change. We can see that it's endothermic. They've told us that again. So remember, endothermic is when delta H is positive. So we need to remember to get that the right way around. And it just wants to say, what does endothermic actually mean? So an endothermic reaction is when you have a reaction that absorbs energy from the surroundings. Okay, that's why delta H is positive, because the energy is going to be going up. Okay, so it's a reaction that absorbs energy from the surroundings. In contrast to an exothermic reaction, which would be one where it releases energy to the surroundings. Okay? And so for an exothermic reaction, delta H would be negative, because the chemicals would be losing energy. They'd be giving that energy out to the surroundings. Okay, part two. What is the value for the enthalpy change of formation of nitrogen monoxide? So that's what's going on here, right? So this reaction is forming nitrogen monoxide, and the enthalpy change for this reaction is plus 66. But the key thing here is, do we know what the definition is for enthalpy change of formation? Okay, enthalpy change of formation is the enthalpy change for the formation of 1 mole of a compound from its elements in their standard states. So here you can see in this reaction, it's forming 2 moles. So forming 2 moles has an enthalpy change of plus 66. Forming 1 mole must be plus 33. So the trick to that one is making sure that you know the definition. It has to be formation of 1 mole. Right, then it wants us to do an enthalpy diagram. So complete the enthalpy profile diagram for the reaction between nitrogen and oxygen. Okay, so we're still doing this same reaction. So it's still endothermic. Okay. We need to add the product, we need to label the activation energy, and we need to label the enthalpy change. Okay, so if this is an endothermic reaction, then the product is going to have absorbed energy from the surroundings, so the products are going to be at a higher energy level than the reactants. Okay, and the products are going to be 2NO, so we can just put that on. Right, and so then this is going to be our enthalpy change, delta H, from the reactants to the products. Okay, but we then need to show the activation energy. Okay, and so remember, it has to go up a little bit higher first, and then it will come down to that level. So the activation energy would be from here all the way up to the top. Okay, so this would be my activation energy. It's usually worth doing, I might just put a dotted line on here just to show where that's coming from. It's usually a good idea to show these arrows just with one arrowhead, because they do have a direction. They are both endothermic processes. So we don't really want to have arrows, double-headed arrows. Do it this way, and you're showing we're going in that direction. They do sometimes get picky about that. And then the last bit here says, explain the meaning of the activation energy. So what actually is this thing here? We've got our enthalpy change there, but we've had to go up a bit more. Remember, the activation energy is the minimum amount of energy needed to start a reaction. So we have to give it a bit of extra energy. That's why we need to give it energy anyway, because it's an endothermic reaction, but we also need to give it a bit extra to get it started. Okay, and so the activation energy, you'd have to give it all of that energy to get it to go. Okay, let's move on. We've got some other questions here. What is meant by standard enthalpy change of formation? Now, we've already talked about this with our definition here on the previous question. So the enthalpy change of formation is the enthalpy change that accompanies the formation of 1 mole of a compound from its elements in their standard states. because it's standard enthalpy change. Okay. And then it wants us to give the standard conditions. So the standard conditions are, in terms of temperature, it needs to be 298 Kelvin, or you could say 25 degrees, doesn't matter what units you use. And the pressure needs to be just normal atmospheric pressure, so it's 1 atmosphere, which is 100 kilopascals or 101 kilopascals. Okay, so you could change the units. Okay, write the equation including the state symbols for the reaction that represents the standard enthalpy change of formation of this, whatever this is, ammonium chlorate. Okay, so we need to do what we've said here, right? We need to form 1 mole of this compound. So we need to form just this at the end. I need to put the state symbols on. So it's forming from the elements in their standard state. So that's nitrogen. So nitrogen is N2 as a gas. But I've only got 1 nitrogen here, so I'm going to have to just have half a mole. Hydrogen is H2 as a gas, but I've got 4, so I need to have 2 H2. Chlorine is Cl2, that's also a gas, and I've only got 1, so I need to have half a mole there. And then oxygen would be O2, and I've got 4 oxygen, so I need to have 2 moles of O2. Okay, and it is really important that you do it like this with the halves in it. You cannot times this by 2 to get rid of the halves, because we must be forming 1 mole of a compound for it to be the standard enthalpy change of formation. Okay, then this question here is asking us about respiration of glucose. Overall equation is the same as a combustion. Okay, so write the equation for the respiration. So what they're sort of telling you this here is, look, even if you don't know your biology, it's the same reaction as the complete combustion of glucose. Okay, so if it's complete combustion, we're going to be starting with this. Do we need state symbols? No, it doesn't say. So we're going to be burning it in oxygen, and it's going to make carbon dioxide and water if it's complete combustion. And then we just need to balance it. We've got 6 carbons, so I need a 6 there. 12 hydrogens, so I need to times that by 6 to get 12. And then I've got 6 oxygens plus 12, so I've got 18 oxygens here. I've already got 6 oxygens there, so there need to be 12 here, so that needs to be a 6 as well. Okay, explain in terms of bond breaking and bond forming why this reaction is exothermic. Okay, so first of all we need to talk about these 2 processes. Bond breaking is endothermic. Okay, we have to put energy in if we want to break a bond. It's going to take effort to break something apart. You have to put energy in. And therefore bond forming is the opposite, so that must be exothermic. Well, any reaction is going to involve, well, almost any reaction is going to involve both of these processes, right? You have to break some bonds and then form some other bonds. So both of these are happening, so it must just be about the balance between them. It's not like only this is happening. So there are endothermic and exothermic processes going on. If it's exothermic overall, then it must be that bond forming releases more energy than the bond breaking. Okay, so it must be that more energy is released when the bonds in the products are formed than was absorbed when the bonds in the reactants are broken. Then it is absorbed. I'll change my tenses here. I thought that sounded a bit dodgy. Bonds in the reactants are broken. Does that make sense? More energy is released when the bonds in the products are formed than is absorbed when the bonds in the reactants are broken. Yeah. We get more energy out from making these bonds than we had to put in to break these ones. So overall, it's exothermic. Overall, it's releasing energy. And the last question on this one is another definition. What is meant by the term enthalpy change of combustion? So we've kind of written the equation here. So this is going to give us a clue. Okay, so it's the enthalpy change. What's important about this is that we've started with 1 mole of glucose and it's complete combustion. Okay, so it's the enthalpy change when 1 mole of a substance, and we can use the word substance here because it's not necessarily a compound. You could do combustion of an element. They will let you put any word. I'm looking at the mark scheme here, and they'll let you put any word in. So if you put element or compound or molecule, they'll let you get away with it. But substance just covers everything. So enthalpy change when 1 mole of a substance, so there's 1 mark saying 1 mole, is completely combusted. Okay, it has to be complete combustion. If there's any incomplete combustion going on, then that won't be the right value for the enthalpy change.